everyone. This is Neha Sisodia, Assistant Professor at New LJ Institute of Engineering and Technology. We are going to see query processing and optimization in our database management system today. So we are dealing with some join strategies that are going to be used in our query processing. So let's go ahead and see what join operations we usually use to perform. There are several algorithms to implement join. So the three of them are nested loop join, block nested loop join, and index nested loop join. So the choice is actually based on the cost estimate we have to perform this join. So let's take an example. Suppose we have a number of records for a customer as 10,000, and with depositor we have this for 5,000. The number of blocks for the customer is 400 and for the depositor is 100. So we have to perform nested loop join in order to get it to compute the theta join. Theta join means with any condition, if we want to perform join between R relation and S relation, let's take two relation which are R and S. So for each tuple TR, so each tuple in R is represented as TR in R, and for each tuple in S that represents as TS. So what we have to do is we have to test the pair, this TR and TS, to see whether they satisfy the condition we have given in the join. If they do, then we have to add this resultant into our join resultant relation. Otherwise we have to leave it like that. So R is called as outer relation because we have started comparing this each tuple of R with the other relationship, and S is inner relation of the join. So what we require here is we need not to do any indices over there. It can be only used with any kind of join conditions we have, but it is expensive since we have to examine each pair of tuples from both the relations we have taken. So let's see how the worst case can be evaluated. If there is enough memory only to hold one block of each of the relation, the estimated cost will be number of tuples in R relation into block size of S plus block of R. So these many disk accesses will be there in order to perform this join. So if the smaller relation fits entirely into memory, so any of them if it is smaller and it can be fit entirely into the memory, we can use that as an inner relation, and the cost will be reduces to BR plus BS disk accesses. So let's assume that what we have said just now, in the worst case what happens is the memory availability cost estimate will be 5,000 into 400 plus 100. So it will be like 20,100 disk access with the depositor we considered as an outer relation. And if we have considered customer as an outer relation, that will be 1,000 into 100 plus 400, that is around 10,400 disk accesses. So definitely we are getting a lesser number of disk accesses when we are taking customer as an outer relation. So if the smaller relation, that is depositor here, fits entirely in the memory, the cost estimate will be 500 disk access. So both of them can be done, but we have to see the cost estimate where we are getting the higher cost. We have to drop that path and we have to take the path with the lower cost estimate to perform this join. So we have a better preferable algorithm which is called as block nested loop algorithm. We'll see this, what this is. So this is a variant of nested loop join in which every block in the inner relation is paired with every block of outer relation. So for an example, for each block we are having BR as a block that are going to be used for relation R. So BR of R, and for each block BS of S. Definitely all the relations will be in certain set of blocks. So we are going to access those blocks first, and then we are going to see the tuples into those blocks. So we will move on to this, and then we have to see this tuple in R and tuple in S. So ultimately what we are going to do here is we have to check whether the condition it satisfies for the join or not. So if it is satisfied, then we have to add it into the resultant. So instead of going through each and every tuple, we only go with the blocks containing those tuples. So what is the worst case estimate for this is number of blocks we have for relation R and number of blocks for S we have plus number of blocks of R. That will be the number of blocks access that we have to make. So each block in the inner relation S is read once for each block in the outer relation. So instead of making each and every tuple to access and compared with the outer relation, we can only make the comparison between the blocks we have access. So in the best case, what happens is we just have the number of blocks of R plus the number of blocks of S. The total of this value is the block access. So we have certain improvements in the nested loop and the block nested loop algorithm. Let's see what these improvements are. In block nested loop, we can use m-2 disk block access. So as what we can do is, as the blocking unit of our outer relation, where m is the memory size of a block, what we have to do here is we have to use the remaining 2 blocks of the buffer inner relationship and output. So in the inner relation, that is the relation here refers to the table itself. So what we have to do is we have to use the remaining 2 blocks to the buffer to buffer actually our inner relation and the output. So the ultimate cost will be BR by m-2 into BS plus BR. So these are the blocks that we have in S and R, and now we have just used m-2 blocks accesses and we are keeping the remaining 2, one for inner buffer and the second for output. So if equijoin attributes form a key or inner relation, then we have to stop the inner loop itself for the first match always. So the scan of the inner loop forwards and backwards alternatively. So what we have to do here is to make use of this block remaining in the buffer, we have to use LRU replacement, that is least recently used policy for replacing these blocks, and we can use index on the inner relation if it is available to us. So moving on to indexing of the nested loop join, as we have seen that can be one of the improvement that can be made in the previous 2 strategies we have seen. So index loop lookup has replaced the file scans if the join is an equijoin or a natural join, and an index is available in the inner relations join attribute. So what we can do for this is it can construct an index just to compute a join. So in order to perform the join, what we can do is we can construct an index to perform this join. So for each tuple TR in the outer relation R, what we have to use is we have to use the index to look up the tuples in S. So that satisfies the join condition of the tuple R, then we have to keep it, otherwise we have to leave it like that. So what are the benefits we are getting here is, in the worst case, the buffer has space for only 1 page of R, and for each tuple in R, we perform an index lookup on S only. So the cost of the join will be BR plus number of relations in number of tuples or records in R into C. Now what this C is the cost of traversing the index, because definitely if we have some index, we need to traverse that index also, and we also have to fetch all the matches that have occurred for S tuples for one of the tuples or R. So C can be estimated as the cost of the single selection on S using the join condition. So if the indices are available on join attribute of both R and S, what we can do is we can use the relation with fewer tuples as the outer relation. So for an example, suppose we have to compute this depositor and customer join with depositor as the outer relation. So let customer have a primary B plus tree index on join attribute and customer name which contains 20 entries in each of the index node. So since what we have here is the customer has 10,000 tuples and the height of the tree is 4, then one of the axes is needed to find the actual depositor for 5,000 tuples. So what is the cost that we can have for block nested loop join? So that will be 400 into 100 plus 100. So that many disk accesses will be assuming the worst case memory we have. So for index nested loop, if we are taking into consideration, we'll be have 100 plus 5,000 into 5, that is 25,100 disk accesses, much lesser than what we have seen in the block nested loop join. So the CPU cost likely to be less than that of what we have in the block nested loop join. So definitely the index nested loop join is always preferred over the other two. Now let's see if there are complex joins, what we have to do. We can have a conjunctive conditions or we have disjunctive conditions. So either we can use the nested loop or block nested loop join, or what we can do is we can compute the result over one simpler join over these join values. So the final result should comprises of those tuples in the intermediate results that satisfy the remaining conditions. So similar is the case with disjunction also. What we have to compute is we have to individually compute the union of the records in individual join that we can perform on R and S. So for each of the condition we can perform a different join and then we can union the entire value that we have filtered out using that join. Now there are some other operations that we need to perform. The one is duplicate elimination that can be implemented via either hashing or sorting. So on sorting, what we can do is we come up with the adjacent values of the duplicates so that we can remove that duplicate. So in optimization, what we can do is these duplicates can be deleted by run generation as well as the intermediate merge step in the external merge sorting. So in the hashing, similarly, the duplicates will come into the same bucket and then we can remove it easily. Similar is the case with the projection, as projection is implemented by performing projection on each tuple followed by a duplicate elimination. Coming to the aggregation part, the aggregation function can be implemented in the manner very similar to duplicate elimination as we have seen. In sorting or hashing, that can be used to bring the tuples in the same group together. What we can do in aggregation function, it can also be applied for each group. So in case of optimization, what we do is we combine the tuples in the same group during run generation and intermediate merges. So what we can do, for an example, if we have count, min, max, sum, we can keep the aggregate values of the tuple found so far in the same group. So while combining the partial aggregate for count, we can actually add up the values at the end. But if we want to perform average, what we have to do is we have to make a separate sum and count values so that after completion of the aggregate values, what we can do is we can divide the sum by count at the end. So this is the most optimized way of performing this aggregation function. Now what about the set operations when we are having union, intersection and difference can either be used as the variant of merge join. So after sorting or variant of merge join after hashing. So let's see what we used to do is set operations using hashing is most preferable. So let's see how it is. So partition both the relations using the same hash functions R and S if we have R1 as a series to 0 and R S1 to N. So each partition I has to be followed by a different hash function building an in-memory hash index on Ri after when we have brought it into memory. So in union, what we have to do is we have to add tuples in Si to the hash index if they are not already in it. At the end of Si, what we have to do is we have to add the tuples in the hash index to the result. Similar is the case with intersection, the output tuples of Si to the result, if they are already there in the hash index, we have to output. Then in the difference, for each tuple in Si, if it is there in the hash index, then delete it from the index. So this actually makes a difference between union and intersection. And at the end of Si, we need to add the remaining tuples in the hash index to the result. So how we can perform the outer join that can be computed if a join followed by an addition of null-padded or non-participating tuples, where the tuples are not participating at all in the join because they don't satisfy the condition. We can either do an addition of this, or by we have to modify the join algorithm itself. So what we have to do is modifying the merge join to compute this left outer join is, suppose we have a non-participating tuple, those are in R minus what we have to select as the values of R from the join. So what we have to modify here to compute it, during the merging, for each tuple in TR from R that do not match in any tuple in S, we have to output this TR and pad it with null values. So right outer join and full outer join can be also computed similarly. We have to keep the respective values as null value. We have to pad what do not satisfy the condition. Similarly, if we modify the hash join to compute this left outer join, the R is a prob relation and the outer non-match R tuples are padded with nulls. So what we have here is, if R is a build relation, when probing keeps track of each R tuples that match to the S tuples, at the end of Si, what we have to do is we have to output the non-match tuples R that has to be padded with null values. They do not match with or satisfy with the join we have performed. Now coming to the complex join, we have join involves in three relations, suppose loan, depositor and customer. So the strategy one that we have to follow is we have to compute the first two and then use the result to compute the another join. And the strategy two, what we can do is we can compute the other two first and then we have to join the resultant value to the leftover relation. So the third strategy that we can perform is we have to perform the pair of join at once and build an index on loan for loan number and on customer for customer name. That also we can do. We can build an index on certain values from the relation. So for each tuple T in depositor, we have to look for the corresponding tuples in customer and the corresponding tuples in loan. So if we are the naive user, we don't know this thing that where we have to satisfy these values. So what we can do is we can keep a value with us and then we can match up all the other tuples with the other relation. So the third strategy actually combines the two operation in one special purpose, and the operation that is more efficient than implementing two joins or for the two relationships. So it is always better to have a pair of join at once where we can build an index on certain attributes of a relation and then we can perform this rather than performing two different joins. So at once also we can have pair of joins and that will be cost effective and efficient. So in the next subsequent video we are going to talk about the optimization techniques. Thanks for watching this video.